Welcome to Math with Professor V. Shout out to one of my Calc 3 students who asked me to go over these two problems from the practice exam. And at first, they might look totally unrelated. One of the problems asks for the equation of a tangent line. It's 39 from the practice exam if you're in my class. And then the other one's a Lagrange multiplier problem, number 47. But both actually come from the same idea, a curve of intersection between two surfaces. So I'll work through, solve them both, and then we can connect the dots, see how gradients really tie everything together and knock out both problems in one go. So here we go. First one, write parametric equations for the tangent line to the curve of intersection of the surfaces z equals 10x squared plus 2y squared and z equals x plus y plus 10 at the point 1, 1, 12. So I drew like a really rough sketch. Z equals 10x squared plus 2y squared. That's a paraboloid opening upward. And then z equals x plus y plus 10. That's a plane, right? Okay. So here's the curve of intersection. And then the problem is fixing a point, 1, 1, 12. And they want us to find the equation of the tangent line to the curve of intersection at that point. So here's the thing. Here's the clincher, okay? This tangent line, we know, is orthogonal to the normal line of a surface at that point, right? This you should have studied when you were looking at gradients and tangent planes and normal lines at that point or at a point. Okay, so I know this tangent line is orthogonal to the normal line of the paraboloid and the plane at that point. So that's the interesting thing. That means this particular tangent line is orthogonal to the normal of both surfaces at 1, 1, 12. So how do I get the normal for each of the surfaces? I could look at their gradients. So here we go. I'll call this first function f and this one g. So I could say f of xyz is 10x squared plus 2y squared minus 1, and the second one, g of xyz is x plus y minus z plus 10. So to get the normal to each of the surfaces, I would look at the gradient of each. We can compute that, no big deal. That's 20x, 4y, and did I miss a z? I sure did. Heavens to Betsy. This is minus z, not minus 1. You were screaming at me through the screen? I know, I'm so sorry. 1, 1, negative 1. Okay. Perfect. All right, so let's think here. Let's think about how to proceed. I have this vector, which will tell me a normal vector to the surface at a point. So will this one. That means if we're interested in 1, 1, 12, the gradient of f at 1, 1, 12 would be 24, negative 1. Gradient of g doesn't change. It's just a plane. Okay, perfect. And here I am trying to write the equation of the tangent line. So I need the direction vector of my tangent line. But notice to this important piece of information. My tangent line is orthogonal to the normal of both surfaces. My tangent line's direction vector is orthogonal to both these vectors. It's mutually orthogonal to both of them. What am I hinting at you to do? Yes, to cross these two vectors, right? Since V is mutually orthogonal, today's not my day to spell, mutually orthogonal to both normals. So take gradient of f, cross it with gradient of g. Oh, we can do it. We can do it. So my direction vector will have components -3, 19, 16. Perfect. So that's the direction vector for my tangent line. And then they gave me the point that it goes through 1, 1, 12, and you can write the parametric equations now. So x would equal negative 3t plus 1, y would equal 19t plus 1, and z would be 16t plus 12. Voila. Good? Okay. Just remember, tangent lines are orthogonal to normal lines, okay? And then since this tangent line was on the curve of intersection, it was orthogonal to both normals from the surfaces. Therefore, it's mutually orthogonal. Anytime you hear mutually orthogonal, you should think cross product, cross product. Okay, next problem. It's a Lagrange multiplier problem, but it also has to deal with a curve of intersection. It says, find the point on the curve of intersection of the paraboloid and the plane that's closest to the origin. So as soon as I see closest, I know it's an optimization problem. I'm trying to minimize the distance, but what's nicer is we use distance squared, right? That way we don't have to contend with the square root when finding derivatives. And I want to minimize the distance from some arbitrary point to the origin. So we would have x minus 0 squared plus y minus 0 squared plus c minus 0 squared. Good? Now, if you were to just proceed as is, that's fine. So this is what we're trying to optimize. So this would be my function, f. And then I would have two constraints. You could call this g and h, and you would have like gradient of f equals lambda gradient of g plus mu gradient of h. And then we would have a system of 5 unknowns, right? X, y, z, lambda, mu. But I pointed out a little shortcut to my class, and I will tell it to you too. Notice here, if I first set up and find the curve of intersection, I can actually reduce how many variables there are in the problem, and it will make solving it so much easier. So let's actually find the curve of intersection. I'm going to solve for 2z in one of the equations and substitute it into the other. So notice here, like 2z equals y minus x. I'm going to plug that in here so that my curve of intersection is x squared plus y minus x, is 4. Oh, so now this curve of intersection combines both constraints, and it also reduced the number of variables to just two. So I could call this g of xy. So why don't we just say we've reduced the number of variables, and I'll just say f of xy is d squared. It's not dependent on z anymore. X squared plus y squared, subject to this constraint right here. And then how many variables will I have? 1, 2, x and y, and lambda, 3. Wow, I'd way rather deal with 3 than 5, wouldn't you? Okay, it won't always work out so beautifully, but because they both had 2z in them, we could eliminate it. You know what I mean? Okay, cool. So here we go. Gradient of f equals lambda, gradient of g, and the rest is really fun. So gradient of f is going to be 2x. Why am I writing 1? Hold on. I got too excited, guys. 2x, 2y equals lambda times, and then gradient of g is going to be 2x minus 1, 2x plus 1. Okay, now it's system of equations time. So 2x equals lambda times 2x minus 1. 2y equals lambda times, oh geez, this should have been a y. I'm just out of control. 2y plus 1. And then the third equation is our constraint equation. So x squared plus y minus x is 4. What I'm noticing is I can solve for lambda in the first two equations, and then I'll just set that equal to each other, right? And then things work out beautifully. So now I can set these two expressions equal to each other. We have 2x over 2x minus 1 equals 2y over 2y plus 1. Yes, cross multiply your little heart out. And we'll have 4xy plus 2x equals 4xy minus 2y. Good. So these cancel. And then I'm left with x equals negative y. So from here, go to equation number 3. So into 3, If x is negative y, we'll have negative y squared plus y squared plus y minus negative y is 4. So this is 2y squared plus 2y minus 4 is 0. So I got y squared plus y minus 2 is 0. Y plus 2 times y minus 1 is 0. So y is negative, oh my god, so wiggly. Negative 2 or 1. Okay, so let's see, x is negative y. So x could be positive 2, y would be negative 2, or x is negative 1 and y is positive 1. And then we got to figure out what z is. So where do we go get z from? I would say go to the plane equation and get it, right? Okay. So if x and y are negative 1 and 1 respectively, z will be 1. And then if they're 2 and negative 2, z will be negative 2. So we have two answers. So which one do I report? Well, what did the problem ask for? It asked for closest to the origin. Which one of these two is closest to the origin? Yes, negative 1, 1, 1. That's the closest one. Closest to origin. The other point is actually furthest, right? Subject to the constraint. But they didn't ask for that. So just tell them negative 1, 1, 1. Good? Okay, I think that was fun. Sorry I solved it so quickly. I'm rushing. I have to go to hot yoga in just a hot second. But two different questions, one underlying theme, the curve of intersection, and we used gradients to solve both, right? We crossed them to get a tangent direction in the first problem, and then we combined them through Lagrange multipliers to find the closest point. Now, if you want a deeper dive, I've got full detailed lectures on tangent lines and planes, Lagrange multipliers, and curve of intersection. So check out the Calc 3 playlist on my YouTube channel, and I'll link some of those videos in the description. And you'll get plenty of practice with step-by-step solutions. Thank you guys so much for your support. Don't forget to give the video a thumbs up. Subscribe. I love you all, and I'll be back sooner than later. Bye.